Hi. In computer graphics we often need the derivatives of complex functions. This video explains how it can be done automatically, without any pain. First of all, a little bit of motivation. I give you an example why we need derivation so often. Here you can see a sea illuminated by a distant light source, and we as virtual cameras are pretty far from the water. The sea is made of water everywhere. So we may ask what the reason is for these wrinkles and waves on the water. Well, the answer is the different normal vectors. So the normal vector has a fundamental effect in shading or color calculations. Normal vector is obtained as a kind of derivative of the surface, so that's why we have to compute derivatives in every graphics application. The other main application of derivatives is the solution of inverse problems. In computer graphics we have a virtual world model, surfaces with equations. For example, this is the equation of a torus. From this definition, using the visualization or rendering process, we should calculate an image that is displayed on the computer screen. The inverse problem of graphics gets the image, and we expect the inverse problem called vision to restore the original objects and their equations. Looking at it a little bit more formally, we can imagine computer graphics as a function evaluation where the input of the function is the model of the virtual world and the function itself represents the rendering process. The output of the function evaluation is the image. So when we consider the other direction, the input will be the image, we know the function, that is the rendering process, and we are interested in the model. So while rendering is a function evaluation, vision is the solution of an equation. Can we solve arbitrary equations? To tell the truth, no. We can solve equations in special cases only, but there is no general strategy to solve any equation, except for a very simple one: trial and error. Trial and error would work in the following way. We take an input value, maybe randomly, substitute it into the function and look at the result. If the computed result is equal to the expected result, then we are done. Obviously it never happens, so we keep doing this trial operation, and if we tried many different options, then at the end we will select that X value which caused the minimal error. Obviously this is a very tiring process. In order to speed it up and give us the hope of conversion, when a particular sample is evaluated, we need to know not only the difference between the computed output and the expected output, but also some hint how to modify this input value in order to decrease the error. And this information is nothing but the derivative. So if the derivative is negative, it suggests that we have to increase the X value, because in this direction the error will decrease. On the other hand, if the derivative is positive, we have to decrease the X value, because in that way we get closer to the minimum where the solution can be found. Not only the sign, but also the magnitude of the derivative present useful information, because if the magnitude of the derivative is big, we can make big steps, because very probably we are far from the minimum of this error function. However, when the magnitude is small, we are at the bottom of the valley, then it is worth making very small steps in order to avoid that we overstep the solution. Many people think that derivative is a simple operation because we can approximate a differential with a difference. It means that when we want to evaluate the derivative of function f at location x, we add a small delta to x, compute this difference and divide the difference by delta. This is called numerical differentiation. I advise you not to use it because it's a very numerically unstable and dangerous operation. Why is it that? Adding a delta value to x means that instead of the tangent, that is the derivative, we approximate this derivative with a second of the function. If the curvature of the function is high, then we can make a pretty big error, especially when this delta step is large. So it's very tempting to use a delta parameter which is as small as possible, but it is also a very bad choice. The computer has just a finite number representation. For example, if we use 32-bit floats, then in decimal number system, a float can represent 7 valuable digits. The rest is undefined or 0. Let us assume that we subtract two very close numbers. In this particular example, the two numbers are different only here, but because of the limitations of the finite number representation, we do not know anything about the digits coming after the last valuable digit. Making the difference, only one valuable digit remains, and all the remaining parameters can be arbitrary with respect to the ground truth. So while we had several valuable digits at the beginning, we have just a single valuable digit at the end. So the error can grow without any limit if we compute the difference of two numbers, and this is exactly what we need when differentials are approximated by differences. Let's see what it means when derivatives are computed. I have taken this not too complicated function and computed the first and second derivatives analytically and also with this numerical derivation scheme. When this delta is 0.1, we can see that the approximation is quite good except at those locations where the curvature is very high. So let us reduce this delta step. When the delta is 0.001, the problem at the high curvature region disappears, but the result becomes hairy, and it will be a complete mess when the delta is as small as 0.0001, because we have lost all the valuable digits in the derivative computation. So the solution is to compute derivatives analytically without any questionable numeric approximation. We could do it on a piece of paper, but this is tiring. Our goal is to do it automatically in a computer program. We want to teach our C++ program to derivate as well. The tool which can be used for automatic derivation is the family of hypernumbers. What is a hypernumber? A hypernumber is like a complex number. In fact, the complex number is one of the members of hypernumbers. We have two real values, x and y, and a symbol I. With these x plus yi numbers, we can do the normal operations that we otherwise do for normal complex numbers, and the properties are also inherited. So for example, when two such numbers are added or multiplied, we can assume that addition and multiplication are commutative and associative operations and so on. We can also assume that when we make operations on these numbers, the result is also in the set of the same hypernumber, so expressed in this particular form. So for example, when two such numbers are added, because of the good properties of complex numbers, we can rearrange the parentheses and express the result in this form, which means that the real part can be obtained by adding the two real parts, and the imaginary part can also be obtained as the addition of the two imaginary parts. And the result is exactly in the same form as the two operands. We have a real part and an imaginary part multiplied by I. What about multiplication? When we multiply two such numbers, because of the distributivity operation, we can break up the parentheses. So we will have x1 times x2, and this is a real value. Then the product of x1 times y2 and y1 times x2, and these products are associated with an imaginary unit I, and finally we have y1 times y2 multiplied by I square. This result should also have the form of the general hypernumbers, a real value and an imaginary part, which is just the product of a real number and I. So we have to say something about I square. If we use complex numbers, the decision is that I square is equal to -1. If we use the algebra of vectors, so I is just the basis vector of a Cartesian coordinate system, then the typical selection is I square is equal to 1 because these basis vectors are unit vectors. No, in order to compute derivatives automatically, we are going to assume that I square is 0. And in that case, the hypernumber is called the dual number. So I is an imaginary number, it's not a real, so it's definitely not 0, but when we compute the square of this imaginary number, the result will be 0. So using the assumption that I square is equal to 0, this last part disappears from the formula of the product. So far we have addition, subtraction and multiplication. What about division? We can apply the same trick as applied to the computation of the division of two complex numbers. So when one hypernumber is divided with another hypernumber, we multiply both the numerator and the denominator with the conjugate of the denominator, and then using the distributive law, both the numerator and the denominator can be rearranged. Again, I square shows up both in the numerator and the denominator, but we already know that these I squares are equal to 0, so these terms are cancelled, so we can obtain a simpler expression, which is also in the form that we have a real number and an imaginary part, which is just the product of another real number and I. Let us recognize that in these operations, the real part is always the same operation as executed for the hypernumber. The imaginary part is not. It looks more complicated, but somehow very familiar. So what are these? These are just the derivation rules. When two functions are added, the derivatives should be added as well. So when the derivative of a product is evaluated, we have to consider the first function and multiply it with the derivative of the second, and then derivative of the first function is multiplied by the value of the second. And this is also the formula for the derivation of a fraction. So it means that our hypernumber can be interpreted as a function in the real part and its derivative inside the imaginary part. The arithmetic rules of dual numbers will be exactly analogous or equivalent to the arithmetic rules of derivatives. This can be implemented in a dual number class, which is very similar to a complex number class, but multiplication and division should be evaluated differently. So in a dual number class, we have a real part and an imaginary part. I denote the real part as f because this is the value of our function, and we use d to represent the imaginary part because this is going to be the derivative value of the same function. In the constructor, we fill up both the function value and the derivative value. With default parameterization, we handle the case when the function is a constant with respect to the derivation variable. In this case, the derivative is 0, which is automatically added by this default parameterization. Using operator overloading, we can define the basic operations So for addition, both the function values and the derivatives must be added. If we want to apply subtraction, function values should be subtracted, derivatives should be subtracted. Concerning the multiplication operation, function values are multiplied, and for the derivative, we use the law of the derivative of a product. For the division operator, function values are divided, and we insert here the formula of the derivative of a fraction. Let us see how it can be used in a real application. First, without any derivation, suppose that we have to evaluate a function f for some value t, and this is just the C++ implementation of the algebraic operation that defines f. If we need not only the function value, but also the derivative for the same value, the type of every variable should be changed from float. The important difference between t and a and b is that t is a derivation variable, so its derivative with t is 1, while a and b are constants, so their derivative is 0. But otherwise we had to just rewrite this expression, replacing scalar values with dual numbers. When the program runs and evaluates this expression, thanks to the operator overloading and the redefined multiplication and division, in the result we get not only the function value, but also the derivative value in data member D. This is nice, but the program is rather ugly. Exploiting the default parameterization, which converts every real parameter into a dual value, assuming that this real parameter is constant, we can express the same formula in C++ with a much nicer expression. So t is a dual number because we will derivate with it. The value of t is the value, and t is the derivation variable, so its derivative is 1. Then I just copy the expression without any modification here, because from A, C++ will automatically generate a dual number using the constructor function equipped with 0 default input parameter. And the same happens with B. So from the point of view of the program, the modification is really minimal. We just replace the float type with the dual number type. And at the end, again, in F, we will have two data members, F and D. F contains the function value, D contains the derivative at the same position. And this is not the end of the story. We can also handle functions, for example, the sine function. Recall how you learned in mathematics what the derivative of the sine function is. So this knowledge should be also transferred to our C++ program. And this can be done by defining new special functions. For example, the special version of the sine function that outputs not just the function value, but also the derivative value. We know that the sine's derivative is cosine, so the implementation of this new sine is just this, which computes both the value and the derivative at the same time. Similarly, if we want the cosine to be used in our differentiable expressions, then we need this new cosine function that tells the program that the cosine function value can be evaluated with the library function, and the derivative of this cosine function is the sine function, for which we can again rely on the library. We may have expressions when these built-in functions or own functions take not just a constant or a derivation variable, but a complex expression like this. So how can we derivate formally when one function includes another function, or in other words, when two functions are composed together? Well, we have the chain rule for that. So when f contains g of t and we want to obtain the derivative with respect to t, then the chain rule should be applied, which means that first we take the derivative of f with respect to its variable g, and the result is multiplied by the derivative of g with respect to t. It means that our sine function or cosine or all other built-in functions should handle not only real values, using C++ terminology, not only float values, but also dual numbers that represent not only the value but also the derivative. And the response of the sine function to this is just the computation of the value. The computation is the evaluation of the sine function for the value stored in g, which is g.f. The derivative of this is just the derivative of the sine function, which is cosine, multiplied by, according to the chain rule, the derivative of the input variable, which is just g.d. We use the same trick for all possible built-in functions. Having done so, we can forget this previous first implementation because our more general implementation incorporates this as a special case. Let's assume, for example, that g is just the derivation variable t. In that case, the derivative is just 1. So when evaluating this for t, we obtain the sine of t in the value part, and in the derivative part, the cosine of t multiplied by 1, which is nothing but the cosine of t, and this is exactly what we had in our first trial solution. So changing the type of parameters from float to dual number, we get derivatives for free. I demonstrate this with an example, and this example is pulse animation. Suppose that on the two-dimensional plane we want to animate an object and force this object to go along a path. It means that this path determines the position of the object, but taking into account that usual objects follow their noses and do not keep their orientation fixed when they are changing the direction in which they are walking, we want this object always to turn into the direction in which it is heading or moving along. So this curve determines not only the position of the object at a particular point of time t, but also the orientation. The orientation is the direction of the movement, which is the current velocity, and the velocity is just the time derivative of the position. Now, let us assume that the path is defined by these two functions. To control the orientation or the heading, we have to compute the derivative of these two functions. The implementation is here. Our derivation variable is t, the time, which is fetched from the clock, so it has a value tt, and as this is the derivation variable, its derivative is equal to 1. Then we copy the definition of the two functions without any modification. Note that we have to use our new sine, cosine, tangent, and power functions because they can handle dual numbers instead of real values or float variables. But otherwise, we didn't change anything at all. So these complicated expressions are evaluated by our program, and thanks to operator overloading, when the computation is finished in variable x and y, we will have the value of these formulae, which are used to set up the position, and in members called D, we can fetch the derivatives of x and y with respect to t, and these derivatives are used to initialize the velocity. The heading direction is just the normalized version of the velocity vector, and knowing where we are and what the heading direction is, the object can be drawn with its right position and orientation. The result is here. We can do it in 3D as well when we introduce a set function that determines the z component for an arbitrary time parameter t. These three vectors together determine the orientation of an arbitrary object. So if we force this orientation onto an arbitrary object, then that object can also be animated along the curve. Thank you for your attention.